today I am going to talk about another new transformation, that is the Mellin transforms. So, Mellin transforms are quite useful in problems related to number theory, in mathematical statistics, and especially in evaluating some asymptotic series in the asymptotic limits, the series sum. In fact, in 1876, Riemann famously recognized the importance of Mellin transforms in his famous memoirs on prime numbers. So, let us start our lecture and discussion today by deriving the Mellin transforms from our Fourier transform. So, consider, to arrive at the definition of Mellin transform, I need to consider Fourier transform. So, consider my Fourier transform. Okay. So, I am given that the Fourier transform of a particular function is, let us say, capital G, which is by definition as follows: negative infinity to infinity e to the power negative I k zeta g zeta d zeta. Okay. And of course, then the inverse of this transform is defined as Fourier inverse of g k, that is equal to 1 by square root 2 pi integral minus infinity to infinity e to the power I k zeta g k d k. Okay. So, if I were to assume, now I am going to make some substitutions now. Let us say this is my 1 and my 2. So, in 1 I am going to assume that my variable I k, my I k is c minus p. Okay. So, let us say my c is a constant. So, then further I am going to assume that my variable x, that is the integration variable x, is e to the power zeta. So, my original variable with which I am integrating is zeta, my new variable is x. So, which means that my original variable zeta is log x, okay, or what I have is d zeta is 1 over x dx. Okay. So, then if I use this all these assumptions in 1, I am going to get on the left hand side I am going to get g of, so k. So, k is, well, c minus p divided by I iota. So, that becomes I times with a negative sign. So, it becomes I times p minus c. So, it was a division by I. So, that brings in a minus sign and hence the reversal of this values. On the right hand side I have 1 by square root 2 pi integral from, this time notice that x, the zeta was from minus infinity to infinity. So, x will be the exponential of that original variable. So, 0 to infinity. So, I have that this is e to the power negative. So, we see that e to the power zeta is x times to the power I k. So, that becomes x to the power minus c minus p. So, that is my Fourier variable, the Fourier function, and g of zeta. So, zeta is log of x. So, small g of evaluated at log of x and dx by x. So, that is my d zeta. So, let me just rewrite this again. So, I get 1 by square root 2 pi integral from 0 to infinity. So, let me just reverse the order here in this power, x to the power p minus c minus 1 log g of log x dx. Okay. So, then similarly if I use a similar substitution in 2, I am going to get that g of log x is equal to, using my inverse transform, the expression in given in 2, I get that g of log x is 1 by square root 2 pi c minus I infinity to c plus I infinity. So, again this is the so called Bromwich contour, x to the power c minus p g of I p minus I c iota, where I is the iota dp. Okay. So, notice this expression. So, let me call this as my expression 3 and I call this as my expression 4. So, in this expression 3, let us now substitute further. So, in 3 what I have is, let me assume another function, assume my function f of x to be x to the power minus c by square root 2 pi times g log x. So, the variation of x originally in this fashion is replaced by the variation in x in this fashion. So, I have just clubbed in most of these terms into a single function here. So, now the 3 becomes the equation, the right hand side expression of the equation in 3 becomes g, it becomes equal to, let me just write the right hand side here, RHS. Okay. So, this becomes equal to integral e to the x to the power p minus 1. So, x to the power minus c is already absorbed in f of x and 1 by square root 2 pi is already absorbed and d of x, and this is from 0 to infinity, right. Now, I call this, notice that this is an integral purely for the function f of x with respect to the variable x. So, I call this as, I am now going to define this integral as my Mellin transform of f. So, this is my Mellin transform of f. So, I denote my Mellin transform with this curly m. So, notice in almost all my lectures I am denoting the transform operator or the transform operation by these curly symbols. So, the Mellin transform with a curly m. Okay. So, this is my RHS of 3. Okay. So, moving on. So, what I have defined is the following. So, my Mellin transform of f is defined as an integral from 0 to infinity x to the power p minus 1 f of x dx, and similarly using my expression 4, using 4 I have that Mellin inverse of f is nothing but the Bromwich contour integral. So, defined by the following integration. So, this is c minus I infinity. Well, let me also call this as the first expression as f tilde. So, m inverse of f tilde is c minus I infinity to c plus I infinity, the Bromwich contour of x to the power minus p f tilde of p dp. Okay. So, that is again just to help you recall, this is not an ordinary integration, this is the Bromwich contour integration that I had briefly mentioned in my Laplace transform lecture. Okay. So, let me just continue using this definition that I have just shown. Okay. So, let us look at some very straightforward basic examples. So, the first question says find the Mellin transform of e to the power negative n x. Okay. Now, to find this we have to evaluate the integral, which is integral from 0 to infinity x to the power p minus 1 e to the power minus n x dx. Okay. So, if I were to substitute my variable t, replace my variable n x by t, then I get that this transformation is equal to integral from 0 to infinity I get e to the power minus t. So, x is, well, t is dt, which is n times dx. So, n can be taken out and this will bring in, well, so after all this simplification I am going to get this is t to the power p minus 1 divided by n to the power p. So, this is nothing but n to the power p times the gamma function of p. Okay. So, the Mellin transform of this expression of this function e to the power minus n x is n to the power p 1 by n to the power p times the gamma function evaluated at p. Okay. So, let us look at another example. So, if I am given the function f of x to be 1 by 1 plus x, so I have to find, or let me just state the problem in another way, show that the Mellin transform of f is this integral 0 to 1 t to the power p minus 1 times 1 minus t to the power minus p dt, okay, or this is also called the function b of 1 p comma 1 minus p, which is given by gamma of p times gamma of 1 minus p. Okay. So, to find the Mellin transform, so the Mellin transform of f is integral 0 to infinity x to the power p minus 1 divided by 1 plus x dx times. So, now I have to evaluate this integral. So, let me just make a suitable substitution to this problem. So, I am going to substitute my variable x with the following new variable 1 t divided by 1 minus t. So, I see that in this case dx is dt divided by 1 minus t square, and I get that this transformation becomes the following. I get, so notice that when x is 0, I have t is also 0, but when x is infinity I have t is equal to 1. So, in this new variable, in this new substitution I have the limit changed from 0 to 1. So, x to the power, so let me just substitute t by 1 minus t to the power p times 1 minus t square times 1 by 1 plus x. So, 1 by 1 plus t by 1 minus t. So, that is my 1 by 1 plus x d t. Okay. So, after all the substitution I am going to get the following expression. I am going to get integral 0 to 1 t to the power p minus 1. So, that is t times another t that comes out, and times 1 minus t to the power, let me just rewrite this as 1 minus p minus 1 dt. Okay. So, that is after all the simplifications, and this is what our right hand side was. So, this is this function b of p comma 1 minus p, right. Okay. So, this is what I had to show. Okay. So, then, and well, there is one more result showing that b is equal to this product of gamma function. This particular result was already shown in one of my lectures on Laplace transform. So, please refer to that lecture. Okay. So, I end this example here and move on. So, then I have to find the Mellin transform of this function. So, the function is e to the power x minus 1 to the power minus 1. So, find the Mellin transform of f. So, the Mellin transform of f is given by, let us say I am going to denote it by f tilde. this is the integral 0 to infinity x to the power p minus 1 by e to the power x minus 1 dx. Okay. So, then notice, so to further evaluate this integral, let me just recall a series. So, recall that the summation of this particular series e to the power negative n x n from 0 to infinity, that is, so this is a geometric series that will give me the following result. This is 1 minus e to the power minus x, right. So, we see that if I were to multiply throughout by e to the power minus x, that is multiplying throughout by e to the power x, the left and the right and the left hand side, I get that this result is e to the power x times summation n from 0 to infinity e to the power minus n x, and what I get is e to the power, well, I get this is, well, let me just not multiply. I think the thing that works here is, I divide throughout by e to the power x. So, that should work. So, let me just divide throughout by e to the power x, and what I get is 1 by e to the power x on the left hand side times this series is equal to 1 by e to the power x minus 1. So, this is the term, the term on the right hand side is what we want, and the term on the left hand side is nothing but, notice that this is, let me just write this series again. So, the series is 1 by e to the power x times the series from e to the power negative n x from 0 to infinity, which is 1 by e to the power x minus 1. Notice that this is nothing but summation e to the power minus n plus 1, well, n minus 1 x, right. So, then let me just say that this new series changes to, so if I plug in n equal to, this new series will change to summation from n 1 to infinity e to the power negative n x. So, I have already divided by e to the power x, and that is given to be the expression on the right hand side, which is this quantity. So, this is the result I am going to use in my evaluation of the transform. So, again coming back, the Mellin transform of f is integral 0 to infinity x to the power p divided by e to the power x minus 1 dx. Now, I am going to use this series. So, I get that this integral is also equal to x to the power p times this series from 1 to infinity e to the power minus n x dx. Okay, because the transformation is quite well defined, I am going to interchange my integral and the series here. Okay. So, the series sum is taken out, and I get that this is integral 0 to infinity x to the power minus p e to the power minus n x dx. Notice that this is nothing but an integral that I evaluated earlier in one of my examples. The first example, this is gamma of p, the gamma function times 1 by n to the power p. So, I get that the Mellin transform is the summation n from 1 to infinity gamma of p divided by n p n to the power p, or I can take this, write this as follows. The term on the numerator is independent of n. So, this is summation 1 by n to the power p from 1 to infinity. Notice that this is my famous Riemann zeta function. So, my Riemann zeta function is defined by this sum. Okay. So, I write this as my gamma of p times the zeta function evaluated at this p. Okay. So, then another example asks to find the Mellin transform of the following trigonometric functions. So, find the Mellin transform of let us say cos kx or the Mellin transform of sin kx. Okay. So, instead of finding the Mellin transform of these values, let me just find the Mellin transform of the corresponding Euler expression. So, we know that Mellin transform of e to the power let us say negative I k x, right. So, I am going to use my n to be negative n to be I times k. So, I know that this is also equal to the Mellin transform. Well, so this is Mellin transform of e to the power negative n x, where n I am going to replace it by I k in one of my previous example. Okay. So, that becomes so that result is already found, this one is already found. So, I am going to use that expression to arrive at the following result e to the power negative I k x, this is equal to gamma function evaluated at p divided by n to the power p, n is I k to the power p. So, this can also be written as gamma function evaluated at p k to the power p times I to the power negative p. Okay, now, I am going to use the pth, the expression, the de Moivre's expression for negative square root 1. So, this becomes well cos, so I is cos pi by 2 plus I, well, so this becomes I, so this is I sin pi by 2 to the power negative p. Okay. So, when I use my de Moivre's formula, I get that negative iota to the power negative p gives me cos of p pi by 2 minus I times sin p pi by 2. Okay. So, which means if I were to take the real part of the left hand side, the real part of the Mellin transform of e to the power negative I k x. So, I know that, well, let me just expand this. This is Mellin transform of cos k x minus I times sin k x. Okay. So, I see that this is also equal to Mellin transform of cos k x minus I times Mellin transform of sin k x. Remember that all the integral transforms must be a linear operator. So, I can just rewrite this function as a linear combination of these two functions. Okay. So, if I were to take the real part of this left hand side, I get that this is also equal to Mellin transform of cos k x, and that is also equal to the real part of gamma of p divided by I k to the power p, which is also equal to evaluating, this is equal to cos p pi by 2. Okay. So, I get that the Mellin transform is of cos k x is cos p pi by 2, and similarly equating the imaginary part, I get that my Mellin transform of sin k x is equal to sin p pi by 2. Okay. Okay. So, what I have is the following. So, let me just move on to the next example.